Hello guys, and welcome back to the final unit of the iGCSE Computer Science syllabus. This is Unit 10, which covers the topic Boolean Logic, and following on from Unit 9, it's another fairly simple and small unit to cover. In today's lesson, we're going to cover the basics behind logic gates, and this term truth tables, which demonstrate the inputs and outputs of logic gates, which will all make sense as we move through the lesson. So as you can see, this is Unit 10, the final unit. Units 7, 8, 9 and 10 are all Paper 2, and the remainder of the units are all Paper 1. If you found problem solving and programming tricky, which were Units 7 and 8, Units 9 and 10, I do highly suggest that you try to best to understand these two units, as you can still pick up a fair few marks in the Paper 2 exam from these two units, which will help you fill in any gaps if you do struggle with pseudocode or the programming questions. So in today's lesson, what we're going to do is look at each logic gate, and by the end of the lesson, I hope that you can identify each logic gate, knowing what each gate looks like, and also knowing the function of each gate, as they all perform different functions, and then to be able to complete the truth table for individual gates and logic circuits, which is a mixture of the different gates that we're going to look at. So I understand this is probably a brand new concept to most of you. It is a topic that's heavily covered under electronics. But just to start off, these are the 6 gates that we need to understand for iGCSE, and as you can see, they all look fairly similar, but there are subtle differences that we do need to pay attention to, and I won't go into detail just now. In the lesson, I will go through each gate, explaining the differences between them and the truth tables to go with each gate as well. So you're probably questioning what actually is a logic gate at this point in time, and as I've mentioned there that this topic is covered in electronics, is because the fundamentals behind a computer or any electronic device are these little tiny circuits inside of these devices, which are comprised of logic gates on a physical level. We've covered quite a lot in terms of binary numbers and how information is represented using a computer, and all this is done by the use of logic gates, as these control the flow of electricity running around a computer, which we know is represented by ones and zeros, which is what we will see today. So in terms of the different logic gates that we will look at, they all do different things. I've said there you can imagine them as little machines that make decisions based on the information that they receive, and then each machine has a different job, and the truth table that goes with each logic gate will determine what that job is. So the truth table chart will show all the possible decisions that each of these little machines can make based on the inputs, which will be ones and zeros. And then something that will become very familiar is that all the gates have 2 inputs, except for one, which is the NOT gate. A NOT gate only has 1 input, which I'm sure you'll get the hang of as soon as we go over a few examples. So 5 of the gates have 2 inputs and the NOT gate only has 1. So as I've mentioned, a truth table is a visual way to show the possible combinations of inputs and outputs for each gate. So here is the NOT gate. The NOT gate is the only one that has 1 input. And as you can see, input A is the only input in this table. And we know that binary is represented in either 2 states, 1 or a 0. So the NOT gate with only 1 input has 2 possible scenarios. Either the input is 1 or the input is 0. There are no other possible scenarios. It is simply either 1 or 0 as the input for a NOT gate. For the other 5 gates, so for 5 out of the 6 gates, these all have 2 inputs, which I've labeled as A and B. And as you can see, with more inputs leads to more possibilities. And essentially, the amount of scenarios that we have multiplies by 2. So instead of 2 possible scenarios with the NOT gate, we now have 4 possible scenarios where A and B can either be 0, 0, 0, 1, 1, 0, or 1, 1. And you will get into habit of seeing these 4 inputs, as the pattern is quite easy to remember, as there are only 4 possible scenarios. Now, the biggest truth table that we will cover is for a logic circuit that has 3 inputs. So this is when we start to combine logic gates together to make a logic circuit, but we are not going to see a truth table with more than 3 inputs at GCSE level. So as you can see, we've now got A, B, and C. And again, the amount of scenarios has doubled again. So instead of 4 with 2 inputs, we now have 8 possible scenarios. Now you shouldn't have to remember this because in the exam, the table is usually filled in. But just in case, a little trick that I like to do is if you see in the first column, we've got 4 zeros and 4 ones. So we've got 4 zeros, 4 ones. And then in the second column, we've got 2 zeros, 2 ones, 2 zeros, 2 ones. And in the final column, it's 1 0, 1 1, 1 0, 1 1, all the way to the bottom. And you might recognize these numbers from your binary chart. So it's 4, 2, and 1, where each number doubles through the columns. But like I've mentioned, there is a high chance that in the exam, this will be filled in automatically, and all you have to do is figure out the outputs. So now we'll look into each gate. And as I've mentioned, the NOT gate is the only gate that has 1 input, which is 2 possible scenarios. And all a NOT gate does is simply inverts the input, which means to swap it round, so that a 1 becomes a 0 and a 0 becomes a 1. That is the only function of a NOT gate, and it simply flips the electric signal around, so it'll convert on to off or off to on. And in our truth table, we demonstrate this by using the 1 becoming a 0 and a 0 becoming a 1. So really simple, and this is the first gate that we'll look at. The AND gate, which you can see here, it looks like the letter D, and as we know, we have a D in the word AND, so that's a little technique we can use if we need to draw the AND gate. And as an AND gate has two inputs, which I'll label as A and B, the truth table has 4 possible scenarios, and as you can see, the 4 rows here are all different, 0, 0, 0, 1, 1, 0, 1, 1, but the outputs relate to the rules of an AND gate, which is an output is 1 only if all inputs are 1. So A and B, so the trick is in the word A and B both equal 1, then the output is 1. So the truth table for an AND gate is that all 1s make the 1. There's only one 1 in the output column, which is at the end. Next is an OR gate. And as you can see, there's a slight curve to it. And the rule for an OR gate is that 1 is output if at least one input is 1. So essentially, A or B can be 1. And if A or B is 1, like it is here, here, and here, then the output will be a 1. So if there's 1, 1 anywhere in the truth table, the output will always be a 1. So slightly different to the AND gate. An AND gate is only when both inputs are 1. And an OR gate, as long as you have 1, 1, then the output will be 1. A NAND gate is short for NOT AND. So when an individual NOT gate flips everything around, a NOT AND gate flips an AND gate around, which if we think back to an AND gate, these were the outputs. And as you can see, the outputs for an AND gate are simply the opposite. So the 0 becomes a 1, 0 becomes a 1, 0 becomes a 1, and the 1 becomes a 0. So that's the easiest way that I can remember. Or if you remember the rule that it outputs 1 if at least one input is 0, then again, you'll come to this output if you can remember it that way. But I like to just simply figure out what an AND gate does and then swap everything around, because a NAND gate is opposite of an AND gate. Following on, a NOR gate is the same as a NAND gate in that it's the opposite of a NOR. So it outputs 1 only if all the inputs are 0. But again, I like to draw my OR gate truth table, which I know is 0, 1, 1, 1. And I can flip them around like so to produce the truth table for an OR gate. Just to quickly mention, a NOR gate is simply an OR gate but with a circle here, and a NAND gate is the AND gate but with a circle here also. So just so you can recognize them visually, there is simply a circle before the output line there. And then finally, an XOR gate looks the same as an OR gate, but it has a second line behind the back there. And an XOR gate is short for an exclusive OR gate, which means it outputs 1 if an odd number of inputs are 1. Now, the easiest way that I can remember is that it's exclusively A or B. So it's A or B exclusively. It cannot be both. Hence why the 1, 1 produces a 0 in the final row. So either remember it as an odd number of 1s, so there's 1, 1 there, and there's 1, 1 in here, and the output is a 1 in both of these, or that it has to be A or exclusively B. It cannot be both, and that's the way that I like to remember. So an exclusive OR or an XOR gate can only be A or B, not both. So now that we've covered each individual gate, now we need to combine our logic gates in order to produce what we call a logic circuit. And this goes back to early on in the lesson, because essentially all electronic devices are built on logic circuits, which is what controls the information that we give it so that we can read it as a human form. So as you can see, logic circuits start to build up and become quite big. Here we've got 1, 2, 3, and 4 gates involved in this logic circuit. But all we need to do, just like the rest of paper 2, is break it down, take our time, and we can decompose these circuits into individual gates using our knowledge of the truth tables in order for us to figure out the overall result of X, which is what we'll need to do in any question that involves a logic circuit. So as you can see, there are 3 inputs like I've mentioned, and the output is labeled as X. So from this circuit, like I've mentioned, we will be expected to produce a truth table. And like I've said, the 3 inputs labeled as A, B, and C allows for 8 different scenarios, which we will see in the truth table shortly. The truth table on the right-hand side, we've got 3 inputs, A, B, and C, and these numbers are filled in like they should be in the exam. And the easiest way to tackle this type of question, guys, is to break it up into each individual gate. So circled here, this AND gate, and a label as an AND gate, we can see that A and B are being input into this AND gate, which will refer to these 2 columns here. Now, to make this a little bit easier, what I'm going to do is I'm going to label the output of this AND gate as D. So D is the output of the AND gate, and then what I've done is I put D into my truth table here, which in the exam you will have a big gap for working space, which is what I recommend you to do. So label it as D and add D to your table. Then what we need to do is we need to recall the rules for the AND gate, and we should remember that A and B both need to be 1 in order for the output to be 1. So the only time a 1 is output will be this row here. So then all we need to do is we need to highlight that in these two columns. And as you can see, it's not recognized here, it's not here. And we keep going. And the only time both A and B are 1 are these two here, which means in the D column, which I've labeled, there are only 2 1s at the very end because there are only 2 scenarios in which the AND gate produces a 1 as an output, which is these circled here. So that's our first logic gate done. We can tick that off and then move on to the next one. So the next gate here is a NOR gate, and I'm going to label the output this time as E. I've done D, I can tick that off, so I'm going to label this one as E. Now just as a reminder, let's write our NOR truth table here. And if you get stuck, what I highly recommend is just draw the truth table to the side of your exam paper. For a NOR gate in particular, I'm going to do the normal OR, which was that if there's a 1 in A or B, then we get a 1 in the output. So this is a normal OR in this column. And then for my output of E, which is going into a NOR gate, I just simply swap these around. So it's 1, 0, 0, 0. So I can scribble this out. And this column is my rule for the NOR gate. So now I'm looking for a 0, 0 for the output of E to be 1. So as you can see, this time I've circled B and C, because if we look at the outputs on the NOR gate, it's the B and the C. The A is going up here, so it's not A that's involved. This time it's B and C. So B nor C, we are looking for 2 zeros to produce a 1. And as you can see, we've got 2 zeros there and 2 zeros there. So in my outputs, I've got a 1 and a 1, and the rest remains 0. Just go back to my rules for the NOR gate. As long as there's a 1 involved, a 0 is produced in the output. So for the letter E, 0, 0, 0, as there are 1s involved here. 0, 0, 0, as there are 1s here also. So as a reminder, guys, just draw your OR gate, draw the truth table for it, and then flip everything around just to remind yourself of the NOR gate rules. Now that D and E are done, we've now got this OR gate, so a normal OR, and if you notice, the lines in this one are labeled as E and D. So now we've got D and E here, and these are going to be the inputs for the OR gate going in this way. So in this gate, we don't look at A, B, or C. We are looking at D and E. And the rules for an OR gate, again, really simple. As long as there's a 1 involved, we output a 1. So the F column, which again I've added, will produce a 1 as long as there's a 1 in these 2 rows here. So as you can see, as long as there's a 1, which is there, 0, 0, 0, 1, 0, 1, 1. Let's just double check. Here's the solution. And then F is now done. So hopefully you're getting the hang of this. And as you can see in the final gate, which is an XOR gate, it's going to be the inputs of F, XOR, and then the C. So this C is coming all the way around from the bottom and going into the XOR gate as an input. So as you can see, I've labeled C and F, and it's an XOR. As a reminder, the XOR gate was exclusively one or the other. So it's 0, 1, 1, and 0. 2 1s produce a 0 in an XOR. We are looking for one or the other in the C and the F columns. So hopefully you can go through, notice that this one and this one, it's one or the other. Yes, F is the only one there, so this would be a 1. C is the only one in this one. This one is 2 zeros, so that would be a 0. This one will be a 1, because there's only 1 1. Again, 1 1 produces a 1, 1 1 again, another 1, and then 2 1s produces a 0. And just to double check, here we have our final output column of X, looking at this XOR gate at the end, producing our final output. So hopefully you had in your head each number as I was going through each row. If not, go back, try it again, and I'm sure this will start to sink in, because once the penny drops in these types of questions, they do start to become really simple, but it's just about breaking it down and looking at each gate individually. Once I show my students of labeling each gate and putting them in the columns here, things do become much easier for them. And again, you are looking at about 10 marks in the paper 2 exam from these types of questions. So the final truth table would look like this. In the middle here would be your working space in the exam, but you can see the outputs of X are labeled here, and this is what the examiner will look at when your exam is being marked. So if I flip back to the learning objectives, guys, hopefully you can now identify each symbol for the 6 logic gates, and you are able to define the truth tables for each one. And just to finish off, if we just quickly go through each one, we know that a NOT gate simply has either a 1 or a 0 going in, and the output would be the opposite. So that's your truth table for the NOT gate. An OR gate has 2 inputs, which means 4 possible scenarios. The output of X for an OR gate is that as long as there's a 1, the output will be a 1. So that's your OR gate there. A NOR gate, I'm just going to jot down to the side, is simply the opposite of an OR gate. So it's 1, 0, 0, 0. Your AND gate needs both inputs as a 1 in order for the output to be a 1. So that's the final column there. And again, a NAND gate, I'm just going to jot down next to it because it's the opposite. And the outputs of a NAND gate are the opposite of the AND gate. Oops, that's a 1, 1, and then a 0. So 3 1s and a 0. And then finally, Similarly, the XOR gate is exclusively A or B. So the first one is 0, 1, 1, because there's 1, 1 here and 1, 1 there. And then the final row, if we remember, produces a 0, which makes it slightly different to the OR gate that we can see here. So the XOR final row is always different to a normal OR gate, which is fairly simple to remember, just as long as you can remember what these 6 gates look like, and we can start to familiarize ourselves with the truth tables that go with them. We are making steady progress, and we will practice the bigger picture, which are the logic circuits, as we move forward. So thank you as always for watching, guys, and I will see you again soon.